Welcome to Maths with EJD. This is another video on statistics with focus on sampling distributions. If you're yet to subscribe to this channel, be sure to do that. Hit the notification bell so you can always get alerted each time a new video is released. And of course, don't forget to comment, like, and share. Comment about the things you like me to teach or a problem you like me to solve. Okay, so let's get to it. Sampling distributions. Of course, by way of definition, a sampling distribution is a probability distribution of a statistic. Now, if you check out the playlist on probability, I dealt a lot with probability distribution, so you can see all that. So a sampling distribution is a probability distribution of a statistic like the mean, proportion, or variance. Okay, so when we have a probability distribution of such statistic, you say you have a sampling distribution, and it is obtained by taking repeated samples from a population. So it describes that is a probability distribution describes the statistic how the statistic would vary if we were to take multiple samples from the same population. So you see, the idea is that, you have a population and then you take different samples of the same population, and probably if you're interested in the mean or the proportion or the variance. So for each sample you take note of the mean or proportion or variance. And if you take like 100 samples like that, you are going to get 100 means, and then you have that's like a random variable like that, and then you can see how the mean or whatever you have taken is going to vary. So let's see some key points with regard to this. So we talk about population versus sample. Of course, in the opening video for statistics, we've dealt with this kind of idea. But to emphasize, let's talk about it again. Population versus sample. So the population is the entire group. The entire group we want to study. While a sample is a subset of that population. So imagine a you have a school, maybe you have a school that has both junior and senior high schools, right? So you can actually take a sample. Maybe you want to look at the academic performance at different levels. So if you take junior school, year one, year two, year three. So for year one, you find their average score, in all of their courses, all of their subjects. You take year two, you do the same. You take year three, you do the same. Then you go to senior school, you take years one, two, and three, find the average for each year. So you're going to get like 6 different values for the average score for each for each of the classes. So, the whole school has 6 classes like that, 6 levels, and then you have the average score for all the 6 levels. So that would be a very nice example of a sample like that. So again, the sampling distribution the sampling distribution helps us understand how the sample statistic, how the sample statistic e.g. sample mean, we talk about population parameters and sample statistic. So how the sample statistic, e.g. the sample mean, how it actually estimates, the population parameter. Of course, corresponding to sample mean would be population mean, e.g. the population mean. So for population, you have parameter. For sample, you have statistic. Okay, so that's one point about sampling distribution, population versus sample. And then we talk about variability. Okay, so different samples will yield different statistics due to sampling variability, of course. So the sampling distribution captures this variability. Okay. Now, an example would be something like this. Suppose we want to estimate the average height of adult males in a city. So if the actual average height is 175 centimeter, we can take several random samples of 30 males. Each sample will have its own average height, Then by plotting the averages of these samples, we can form a sampling distribution. A sampling distribution of the sample mean. Okay, so that's the idea. So let's move on to talk about another important part, importance of the central limit theorem, importance of the central limit theorem. Under the playlist on probability, I've dealt with the central limit theorem also. So you can also refer to that for a hint, for maybe additional information, so to speak. So let's talk about okay, before we go to that, right? Importance of the central limit theorem. So the central limit theorem, what you can call CLT, states that for a sufficiently large sample, the, 'the' 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 ' for a sufficiently large sample size. Usually, now in statistics, we would consider any sample that is greater than or equal to 30 to be sufficiently large. So the sampling distribution of the sample mean will be approximately normally distributed. Okay, that is regardless of the original populations, regardless of the original populations distribution. Provided the samples are independent and identically distributed. Okay, that is IID, independent and identically distributed. Okay, so what are the key points about this then? Are the key points about central limit theorem? So first, we talk about normal distribution. So the CLT, the central limit theorem, is fundamental because it allows us to use normal probability. It allows us to use normal probability theory to make inferences about population parameters even when the population itself is not normally distributed. Okay, so the central limit theorem helps us a lot. Even when you have a population that is not a population parameter that is not normally distributed, the central limit theorem can help it to use normal probability to estimate. Okay, and we have standard error. Of course, standard deviation is for population, standard error is for your sample. So the standard deviation of the sampling distribution which is also known as the standard error, is calculated as the population standard deviation. It's calculated as the population standard deviation divided by the square root of the sample size. So we have that standard error, which is the standard deviation of the sample, standard error, which you can call standard error, which you can call SE, is the standard deviation for the population and divided by the sample size. That is what you have for that. Okay, so we can also talk about implications. Implications for hypothesis testing. Yeah, that's the third key point for central limit theorem. So the central limit theorem enables hypothesis testing, and the construction of confidence intervals based on normal distributions. Okay. And of course, we can take some examples before we bring everything to a close. So example one, we have non-normal population. Non-normal population. So that's central limit theorem helps a lot with this, like we've said already, for non-normal population. So consider a population of incomes in a city which is highly skewed, That is, most people earn low incomes with a few high earners. Okay. If we take a sample of 50 incomes, the sample mean will be normally distributed due to the central limit theorem, allowing us to apply normal probability methods to infer about the population mean. By the way, I did not remember to tell you that starting from this video, we are considering inferential statistics. So sampling distribution is the first topic under inferential statistics that we are considering. Okay, so let's talk about confidence intervals now. Confidence intervals. So if the sample, if the sample mean income from the previous example, is $50,000. So you see from the example above, right? We've said for sufficiently large sample size, right? And 50 is considered sufficiently large because sufficiently large is when you have sample of 30 upwards. So based on that, I want to talk about the sample size. So confidence interval. If the sample mean income from the previous example is $50,000 with a population standard deviation of $10,000. So we can calculate the standard error as follows. So of course, don't forget the formula for standard error is sigma, that's population standard deviation divided by square root of n. So, and we know already that the population standard deviation is $10,000 and the sample size is 50. You know, that's 50 that we saw in the first point. So in this case, we can calculate the standard error to be 10,000 divided by square root of 50, and that is approximately 1,414.21. So using the standard error now, using this standard error, we can actually construct a 95% confidence interval for the population mean. So in that case, we have confidence interval would be equal to sample mean. Okay, I want to get more space, so I need to use that wisely. So we have confidence interval is equal to sample mean plus or minus z times standard error. Okay, of course, where z is actually the z score. It's the z score which corresponds to z score corresponding to 95% confidence. And if you check from the table, that is approximately 1.96. Approximately 1.96. I think starting from 2 videos from now, I'll be talking about the table we'll be using for this. So you can see how we arrive at the 1.96 in case you don't know already. So now we can say, therefore, 50,000 plus or minus the Z score, which is 1.96 times 1,414.21. Okay. So if you do all this now, you'll discover that this 50,000 plus or minus, plus minus this product, right? It will give you something approximately 47,500, then against 52,500. So this is the interval. So if you subtract this, you get this. If you add it, plus or minus, if you add it, you get this. So that will be the interval for the confidence interval based on what we have. So in conclusion, okay, let me just go ahead and write this. In conclusion, right? In conclusion, okay, understanding sampling distributions and the central limit theory is crucial in statistics. It's crucial in statistics because they form the backbone of inferential statistics. Now, there are 2 types of statistics, right? Descriptive statistics and inferential statistics, allowing researchers to make valid conclusions about populations based on sample data. Okay, the CLT's ability, the central limit theorem's ability to normalize the distribution of sample means makes it an indispensable tool for statisticians, especially when working with large sample sizes. And don't forget, large sample size starts from 30 and it goes up like that. Okay, so that is how it's been here, talking about sampling distributions under inferential statistics. Be sure to subscribe to the channel, hit the notification bell so you can always get notified each time a new video is released. And don't forget to comment about what you like me to teach, what you like me, a problem you like me to solve. Then like and share so that more people will have access to all this learning. Thank you so much for always taking your time to do this. See you next time. Bye.